Before going to that uh, further explanation about the reactance relay, just we'll have a recall about the first relay, which is a simple impedance relay. So again, I'll recall the distance relay is having it's a family of three relays. One is simple impedance relay, a reactance relay, and more relay. So just now in the last few classes we saw the simple impedance relay, where the operation of the relay totally depends upon the set seen, impedance seen by the relay. If it is less than the set, it is going to operate, and it's having a characteristics of a circle characteristics, which is covering all the four quadrants in the RX diagram. And from the universal torque equation, we derived the triple law by assuming the constant of torque produced by the current or in the current coil, assuming it as positive, and the torque that is produced by the voltage or potential coil, assuming it as negative. Negative means here it is going to produce a restraining torque, and omitting the torque produced by the directional unit. Okay, this is what the triple law we saw, and the implementation, simple implementation of that relay SIR, simple impedance relay, is the balanced beam structure using electromagnetic attraction type of relay. Then we analyzed certain characteristics of the relay. Just we checked whether the relay is going to operate during the normal load condition. Positively, it is not operating during normal load condition, okay, which it should not do. The next one is we saw directional property, and since its characteristics fall in the third quadrant also, 1 and 3rd quadrant. Thereby, it is going to operate for both for the forward fault and the reverse fault, which is 180° out of phase with respect to forward fault. It is going to operate. So thereby, it is not having any directional property. That is what we understood. Then, usually in the beginning itself, we told the fault through an arc, which is having some resistance, can be estimated using the empirical formula given by Warrington. In case if the fault is accompanied with an arc having that resistance, then there will be a underreach in the relay. Okay, particularly in the simple impedance relay, there is an underreach that we saw. Reach is reduced. Reach is that I think it is the farthest fault location with respect to the relay installation, which a relay can sense. That is nothing but the reach that will be reduced. Finally, during the power swing, in case of outage of any one line out of the two parallel lines, which is transferring the power from source to load, in the loss of one line, there will be a swing in the del in order to move from the initial value to the new equilibrium value. While doing so, there is a change in the impedance seen by the relay whenever this del is swinging. We understood that one using the graphical method, how the increment in the del affects the impedance seen by the relay, which will progress towards the characteristics or towards the operating region of the relay, simple impedance relay in the RX diagram. Thereby, the chance of operation of the relay during the power swing is very high, which is not good actually, because most of the power swing or stable power swing, it will come to a new equilibrium state and everything will be stable. But in case if the relay sends this as abnormal operating condition and it operates means, then it will land up in a instability of the whole power system. This is what we discussed in the simple impedance relay. Moving to the reactance relay, another member of the family distance relay. It is reactance relay. Name itself, it is, you can understand. Here, instead of impedance, the relay is going to sense the reactance. So impedance into sine of angle, right? So for this, again we are going to take two components. One is current component, which we are considering. Current component means torque producing component, current coil. We are going to assume that current coil is going to produce the positive torque, operating torque. And instead of voltage coil, we are taking the directional units, which will have that both V and I cos of tau minus theta. So that directional unit, that component we are taking, and we are considering it as a restraining. It is going to produce a restraining torque. In that, assume if you adjust and bring the tau maximum torque angle. Maximum torque angle is nothing but the angle between the voltage, the two fluxes to be equal to 90 degree. Okay, whatever the angle between you have to adjust the angle between the voltage and current injected to the directional unit to make the two fluxes to be at 90 degree. Okay, flux produced in the current coil, flux produced in the potential coil. We should bring it at 90 degree. That is nothing but tau. So from that we saw that Z scene can be converted into X scene. Okay, after multiplying it with this one cos theta minus tau, making tau is equal to 90 degree, you will get Z scene sin theta, which can be written as X scene. So once you are considering the reactance is observed by the relay, means then its threshold value should also be represented using X value only. So instead of Xh, it has been noted as Xn. Both are same. So when X scene is less than Xn, it is going to trip. Now for this condition, in the same Rx plane, if you want to plot the characteristics of this particular reactance relay, since it is going to consider only the imaginary part of the impedance, which is the y-axis. Always we used to consider imaginary values in the y-axis, real values in the x-axis. That is why in the Rx plane we are taking R in the x-axis and x in the y-axis. Now this statement of the trip law shows you the characteristics is nothing but the distance from 0 in the Rx plane up to a certain xn, the threshold value in the x. Since it has not mentioned any value about R, so infinite line can be passed through that xn, okay, that magnitude in the y-axis. That line can be a horizontal line and it is an infinite line going through. 1 minute, sorry. Yeah, it's going through. Now we are incorporating the usual way, the fault characteristics of the line fault characteristics we are incorporating on the relay characteristics, as we did for the simple impedance relay. Here also we are incorporating, and we have to show the area up to which the relay will operate. So it is clear that below the xn value, so xn may be 5 ohms or 10 ohms like that. Below that value, whatever the value of x is there for any kind of fault condition, x seen by the relay, if it is less than xn, it is going to operate. So all these areas, completely all these areas are trip region. The whole minus x values are trip region, whereas above this it is restrained, right? And at the end of my last class I told you may think about the analysis about the relay operation of the relay during the normal load condition. So far for any other relay we have not discussed that. Only when we started the distance relay, but we started with analyzing for normal condition whether the relay will operate or not. It is a peculiar analysis we did. Reason you can understand here. For simple impedance relay, I think you might have understood that whether the relay is going to operate or not during the normal load condition. We saw, yeah, this diagram. So the normal load impedance is this point. If the load is R minus Jx, if the load is R plus Jx, it will fall here anyway. But the impedance is fall very far away from the characteristics. Thereby the relay is not going to operate. And comparing with your reactance relay, the area or the region of the area where the relay will operate or trip region is very small compared to that a reactance relay. Now coming to the same point, you just think over the same point. Sorry, 1 minute. Think the same point. Now place the same point in the relay reactance relay characteristics. Yeah, reactance relay characteristics. Let us assume it is coming somewhere here or here, whatever. Okay. Now, if you place here or here, whether it is under the trip region or not, it is under trip region. So the relay is going to operate. Reactance relay is going to operate for the normal load condition. Then what kind of relay it is? Then why they accepted this innovative relay? It's an innovation, like with respect to the simple impedance relay, some improvement they did. But what kind of improvement it is? See, it is going to operate for the normal load condition itself. When compared to the simple impedance relay, that relay is far better than this one. It is not going to operate during the normal load condition, but here it is going to operate during the normal load condition. But there is a very big advantage of this reactance relay. Then using this concept of reactance relay, they made a hybrid with the other relays. They incorporated this relay, this idea of this relay along with the other relays. What is that much important advantage here is, like our simple impedance relay, there is no disturbance over the reach of the relay. Whatever the arc resistance is there, whatever the arc resistance is there in the arc, the fault with an arc with any amount of resistance, it doesn't bother the reach of the relay. Reach of the relay is fixed. This is a peculiar feature observed in the reactance relay only. It is not found in the Moore relay also. Similarly, it is not found in the simple impedance relay also. Okay. Now coming to the implementation. So this implementation is explained with a induction cup structure. This is one kind of electromagnetic induction type of relay, like our watt-hour meter. We saw familiarly watt-hour meter, particularly for IDMT type of relays and all. We saw watt-hour meter. I think you remember that name, watt-hour meter, shaded pole structure, induction cup structure, like that. Here it is an induction cup structure. So you can see the operating coil, which is the current coil. Okay, and the pressure actually the other part should be the directional unit. So these all directional unit only, right? The restraining coil or pressure coil. So the voltage will be applied here. Now the current, it is fed to the operating coil as well as these polarizing coil. Here the word polarizing means which is determining the directional unit. It is relevant to the directional unit, even though it looks like it is in series with the operating coil, but it is involved with the directional unit. Okay, that you have to understand. See, I think you remember, for the directional unit we need to inject both the potential voltage as well as current. So the voltage is injected to the corresponding pressure coil and the current is injected to the current coil. But here already we are using a current coil to produce the operating torque. In order to have a discrimination, it has clearly mentioned the name. Here it is operating current coil and this is polarizing current coil. Okay. So a 4-pole structure, and thereby 2 fluxes are going to be produced, which is going to make the resultant torque on the disc, which will make the plunger to move in this direction. When in this direction means when the operating coil torque is more than the restraining coil torque. If restraining coil torque is more than the operating coil torque, it will come back, it will travel back. So in order to implement this, the reactance relay, we need again both CT and PT. This is general. For a distance relay, we need both the instrument transformers CT and PT, no other way. So just now we discussed about this normal load condition. It is going to make the relay to operate, which is very worst performance of the relay. Now, why it is tolerated? Why this worst performance of the reactance relay is tolerated means the reach of the relay is not disturbed by the arc resistance in the fault. Okay, you can see that. Now, initially, let us assume AB line is the line fault characteristics when there is no arc in the fault. Now, for the second case, let us assume there is an arc in the fault path with an arc resistance equal to BC, because C, just keenly understand the word I'm using, arc resistance. I'm not using arc impedance, it is an arc resistance. Arc is nothing but current flowing through the air, ionized air as a path. So there, when the current is passing through that ionized air, resistance will be very high. So you will see the spark. So the dissipation of the electrical energy into heat energy was clearly seen using the NAC diagram. Okay, so that is why it is resistance. You should know the basic fundamental. So now the BZ is the resistance, okay, of the arc. In case if BZ is the resistance of the arc, now the line actually it should be drawn parallel to B. Another line parallel to B crossing C. You have to draw a line. Now this is the total characteristics of the fault. Characteristics of the fault. But now also see the reach of the relay of this reactance relay. Initially it was AB. Now also it is same distance in the C and B are on the same line. Whereas in case of the simple impedance relay as well as in the Moore relay, we are going to see the Moore relay also. In both the cases, as the relay, the characteristics operating region is curved one. It is curved one. So thereby these 2 points won't be in the same line. It cannot be in the same line. That is why some underreach we are noticed in those type of characteristics. Whereas that type of underreach is not here. Reach is not at all disturbed by the resistance of fault path. This is the very major advantage of this relay compared to the other relays. Okay, or otherwise they would have discarded this relay, this idea of incorporating this concept. Yeah. Now, so again, directional property, that is the other important analysis we used to carry out. Again, you can draw a line just 180 degree out of phase. With respect to AB line, you can draw another line just like this in the third quadrant. Again, this line falls in the trip region only, that is in the third quadrant. Thereby, this is also not having any directional property. It will act for both for forward fault as well as for the reverse faults. Both the faults it is going to operate. Right. Now, so that is what this diagram shows you. Extending that line BA in the third quadrant, you can see if you consider this as the forward fault characteristics, this will be the reverse fault characteristics. So the relay is not having any directional property. Directional property of the relay is non-directional. Does not mentioned here. You can assume. Now, similarly, again the power swing. Just now we saw the power swing in an elaborate way. We saw here in a simple way it has been given, right? But in the picture you can see the assumption what I used. I assumed actually. I think you remember the assumption. I can recall that the impedance, internal impedance of the or the synchronous impedance of the alternator and the load, I consider it is reactive. XBR ratio is high, so I consider it as reactive. Neglected resistance. So thereby my, I think you remember that my ZSA, while I'm plotting in the graph, I plotted it in vertical way with respect to X for my easy understanding, right? To explain you in easy way. Similarly, XB also I have taken parallel to Y axis, means that I omitted resistance. Whereas I didn't did that XL. XL, I cannot omit resistance. It is significant. In the ZL, in the impedance of the transmission line, Just like that, I cannot omit the resistance as it is very significant because that much lengthy line of a not a that much good conductor also. Probably we are using ACSR, aluminum steel reinforced. That only we are using aluminum core steel reinforced. So which will have some more resistance. So we cannot omit it. That is why we have taken the exact XL. Okay, the summation of XL and XA, XB is nothing but X ZT, which is not shown here, ZT. ZT. So this is what this graph shows you. And see, we found the Z in that diagram. I think you remember. I mentioned it as OP, which is nothing but minus ZSA plus EA at an angle del divided by I think 1 minute. I will go there. I also forgot that expression. Yeah, by R. E at an angle del by IR seen by the current seen by the relay. Yeah. So this is the OP. Again, during del in the increment of del during swing power swing, del is going to increment. In that case, OP this P point, this point is going to travel towards this direction from right to left in this direction. This is going to occur normally, generally. Now here, if you incorporate your reactance relay characteristics, just a straight line like this, put a straight line parallel to x-axis, put a straight line, that is your reactance characteristics. Now also see, you can see that the increment in the del is going to make the reactance to come inside the operating region of the reactance relay. Thereby, this relay is also prone to operate during the power swing. So during the power swing, it cannot escape. It is going to operate. For normal load condition, it is itself it is going to operate. Means what about power swing? It is going to operate. Any doubt up to this? Is it clear? So now we have to explain the last relay in the family of distance relay, which is the Moe relay. I think you know what is meant by Moe. Reciprocal of Ohms. It is nothing but Moe. So this type of relay, it has been developed. Now to what is the main idea is whatever the some drawbacks is there in the reactance relay and the simple impedance relay can be overcome here. Probably like both the relays what we saw earlier is not having any directional property. So now you can incorporate a directional property here in this relay. The next one is we have to avoid the operation of this relay during the normal load condition as well as the probability of operation of this relay. See, I'm not saying this relay won't operate during the power swing, but the chance of the operation of the relay during the power swing is least compared to the other two relays. We are going to see that it is least compared to the other two relays. And what about the reach of the relay? Means it is better than the simple impedance relay and worse than the reactance relay. Okay, how I am saying it is better than the simple impedance relay means there the percentage of underreach is high compared to the percentage of underreach in the Moe relay. That we are going to see. Okay. Now, as usual, we are going to start with the universal torque equation. So here, now in this case, we are omitting current coil, which is usually we consider it as operating torque, producing operating torque. We are omitting that, and we are considering the directional unit as the component which is producing the operating torque, and the voltage coil, potential coil, we are going to treat that as restraining torque. It is going to produce a restraining torque. So what I mean by that is K3 we are making positive, K2 we are making negative, K1 we are making 0. So by doing so, you will get an triple. You can write the equation like this. This equation, it is based on what you are assuming. Based on that only we can write this equation. It is nothing but when it will trip. That is what the meaning. When it will trip means out of these components, which component you considered the that as operating torque, it should be greater than the which you consider it as restraining torque. So here I considered this K3 VR IR cos theta minus 2 as operating torque. So it should be greater than the restraining torque, which is nothing but the K2 VR square. Now again, as usual, we are going to rewrite like this. Now you can simplify these equations. You will get VR by IR. VR by IR should be less than or equal to K3 by K2 cos theta minus 2. Like this, the equation will become. So again, here it is nothing but Z seen. VR by IR is Z seen. It is almost same as that of the simple impedance relay, but not exactly the same. It is different. Why it is different? Because the threshold value, it is simply Z set there, but here it is Z set cos theta minus 2. Okay. So thereby it is not a simple circle covering all the 4 quadrants in its characteristics. It will be a characteristics like this. Okay. Because Zn cos theta minus 2, only this area is this area. 1 minute. Only this area, shaded area, is the operating torque. Within this, okay, within this theta minus 2, within this area, it is not going to trip. Outside also, it is not going to trip. So this is your ZR. If it is less than Zn cos theta minus 2, if it is less than Zn cos theta minus 2, that is this area. Okay, completely this area is the trip region. However, inside the circle itself, there is a particular area, what I am showing you, that in that ZR is more than Zn cos theta minus 2. It is more than that. Thereby it is not going to operate. Even it is not going to operate in the outside. This is what the Moore relay characteristics. And see here, this characteristics is not covering third quadrant. Thereby directly we can say it is having a directional property. It is going to operate only for the forward fault. Okay. Now if you incorporate the line characteristics here, okay, and you extend the line characteristics in the third quadrant, which is the fault characteristics, that is reverse fault characteristics. If you consider this as forward fault characteristics, this will be the reverse fault characteristics. Now that reverse fault characteristics is falling on the which region? It is restrained region. So the relay is not going to operate. One thing. With this diagram itself, we can discuss about the other qualities also. Similarly, now where will be the load, normal load? It will be somewhere here, where my cursor is pointing, or somewhere here. Anyway, surely it will be outside the characteristics. And if you see the trip region compared to both reactance relay and the simple impedance relay, it is very small, very small. Thereby, since it is small, the reason. So previously I told that the chance of operation of this relay during the power swing is less. That is what I told. Why it is less? What is the reason? Is because the region which it is covering, the trip region which it is covering, is so small as compared to the simple impedance relay and the reactance relay. So here also similar to the, since we are having a directional unit, we are following the same implementation of the reactance relay, which is structure. So here the operating current coil, polarizing voltage coil, two polarizing voltage coil and operating current coil, all together it is going to produce, is going to act as a directional unit. Another restraining voltage coil is considered coil. Name itself it is clear, restraining coil. So again here also, what are the things we need? Means only voltage from the potential transformer and current from the current transformer. It is enough. Okay. Yeah. So as I told already, the same thing here also. There is a underreach. There will be an underreach. See now, if again the same thing. Previously, for the first case, if you are not considering any arc in the fault path, which is OA. Now once you consider the resistance in the arc in the fault path, which is BC. Now the width of the line becomes like this. So thereby, if you extend this line from C towards this line, it will be in the B point. Thereby, there is an underreach. How much underreach? AB by OA. This is very small compared to the simple impedance relay. So related with these things like underreach of the other three relays, we are going to see some one or two problems. It will look like a design problem. We'll see that in the next classes. Now, as I told, it's directional. It is having a directional property. It is going to operate only for the fault because they expanded like this. Okay, the curved part they expanded like this. So just it is clear that it is going to operate only in the first quadrant and little bit of fourth and second. It is not in the third quadrant, so the relay is not going to operate for the reverse faults. Yeah, so same thing, same diagram, it is incorporated here. During the power swing, the locus of the power swing means how the Z is going to move with respect to the change in the del. That is what shown here. It is going towards this one, but the probability of chance of entering this region is less. Thereby, compared to the other two relays, chance of the operation of the relay of this relay is less. So this is what the left portion in the alternator side. This relay, more relay only, it is used in the protection of alternator against loss of excitation. We already discussed about the problem of loss of excitation. It comes under abnormal operating condition. It is not considered as a fault condition in the alternator. Instead, it is considered as an abnormal operating condition. Because without loss, without excitation, also the alternator can continue to operate and delivers real power and absorbs reactive power. But it cannot operate as an alternator. Instead, it will operate as an induction generator. Thereby, it will get overspeed. Okay. So it is going to consume the reactive power and it is going to deliver the real power. So sensing the field current, by sensing the field current, you cannot understand that there is a loss of excitation, because through induction there will be a current in the rotor. Through induction also there will be a current in the rotor. Okay. So since the existence of the current in the rotor will lead to misinterpret about your loss of excitation. That is why we have to concentrate on the stator side. In case of stator side, it is clear that since the reactive power generated by the alternator is completely failed, and it depends, for the reactive power, it depends upon the grid. Since it is connected to the grid, it will take the reactive power from the grid. It cannot generate the reactive power because, see, this I already discussed anyway. I will just recall you. Alternator is a component, is a machine, as a device which is going to produce real power as well as reactive power. So how it produces the real power means with the help of the inputs, which is the mechanical inputs from the. How it produces the reactive power. In this way only you have to understand how it produces the reactive power means by the excitation provided to it, field excitation. With the help of the field excitation, that is a DC supply, what it is provided to produce a magnetic field. Magnetic field in the fed to the machine only is going to make the device to produce the reactive power. Once the reactive power is produced by the alternator, the voltage, terminal voltage will be rated voltage. In case of loss of excitation, there are many reasons. We already discussed about reasons for the loss of excitation. When there is a break in the from the DC side, DC supply side, from the generator side, or like that. Loss of excitation for the DC generator, which is acting as a source for the field of alternator, is also one cause. Like that, so many causes are there. In that case, whatever the stator current is there, from that it is going to induce an EMF in the rotor coil, and thereby it is going to act as an induction generator. But when it is acting as an induction generator, it is going to run in high speed. So it is going to take the reactive power for the production of magnetic energy. It is going to depend on the grid, right? Because it is connected to the grid, some other source will be there, many sources will be there. It may be one of the alternator in that grid. So the other alternators may support. Okay, if it is feasible, it may support for the thing. But even though it is supporting, your terminal voltage will drop a lot. Terminal voltage will drop, but the current in the line stator windings will increase. So this will cause a sudden decrement in the impedance. Z will decrease. So this idea, the decrement in the impedance seen at the stator side can be utilized for sensing the occurrence of this abnormal operating condition, loss of excitation. Thereby, by incorporating an impedance relay on the stator side of the alternator, we can easily check whether the loss of excitation is occurred or not. Once the impedance seen by the relay, which is installed near to the alternator, goes less than the Z set value, Z set into, because here we are using more relay, Z set into cos theta minus tau, immediately the relay is going to operate. One minute. Yeah. So this is what the relay called Moe offset relay. This is a special kind of relay used to sense this change in the impedance on the stator side of the alternator. But you can see the little bit the characteristics of this Moe offset relay is changed. Okay. Because in the stator winding, even though in the explanation I told Z, but actually here again X is important. Just now I explained for the power swing, even though I plotted ZSA and ZSB, I assumed it as to reactive. Here also assuming like that, the transient and subtransient reactances are assumed here. Okay. And you can see how the reactance value, reactance value without any abnormal condition and during abnormal condition, how it travels inside the trip region. That is what shown by the three curves. No need to confuse it. It is showing during the rated initial output, medium initial output, and low initial output. During the three different conditions, whatever the reactance was there at that time, how it moves, how it varies and reaches this point. That is what shown here. Okay, the locus only it is shown here. All are coming to this area, which is the trip region of the Moe offset relay. Okay. So it is a simple comparison of all the three different impedance relay, whatever we discussed. So the table is made like this based on the which quantity you are considering as it as operating quantity, restraining quantity, directional property, performance of the on load, effect of fault resistance on the reach of the relay, area occupied in the RX plane, effect of power swing. So for the simple impedance relay, operating quantity is current. Similarly, reactance relay is also operating quantity is current. We saw current component we consume current coil we assumed it as operating coil, whereas Moe relay directional element we use directional element as operating quantity. Restraining quantity in both simple impedance relay and the Moe relay we used voltage potential coil, whereas in the reactance relay we used directional element. Similarly, directional property except Moe relay, the remaining two are not having any directional property. Performance of the load except reactance relay, both are restrained. Simple impedance relay and the Moe relay. Effect of fault under fault resistance means arc resistance both simple impedance relay and more relay under reaches, whereas this one reach is unaffected. And area occupied on the RX plane, moderate, smallest, very large. So since it is smallest, small operation during the during the power swing is less as compared to the simple impedance relay, whereas these two small operates. Now, so far we saw all the distance relays, all the three types of distance relay. Hereafter, we have to understand in what way we have to connect the real-time line, how to connect it to that. Okay, like see what is the meaning is how we connected our directional or current relay. What are the appropriate voltage you have to line voltage you have to feed to the potential coil, and what is the current you have to feed appropriate such that it sends the corresponding fault current in the corresponding phase. In the same manner, here also we have to search for the ways how to do the connection. Okay. I think it is 4 or 5 slides. We'll try to complete it. So the implementation of the distance for the following. In this way, we have framed the idea. How we are going to provide protection against all the tension force. The first thing is you should know what are the tension force. Can anyone say what are the tension force? So it is going, you see, we are going, it is, I think it is clear that we are discussing the distance relay, which is going to be incorporated to provide protection for the transmission line. In the transmission line also, there is a possibility of all the tension faults. What is a tension faults? Line to ground, double line to ground, and all the line to grounds. If you see for each and every phases, you will get tension faults. Means what I mean by that is R to G, Y to G, B to G. You understand? R to Y, R to Y to G, R to Y to B, Y to B to G, like that. Like that I am asking you to see. Then you can find tension faults. Now we want to provide protection for, we have to sense all the tension faults. Whatever the fault occurring, it should be sensed by the relay. For that, in what way the CT currents and the PT voltage will have to be processed? How we have to process it? Next question is, can a single distance measurement unit, only one, if I use only one impedance relay, whether it is feasible to sense all the phase and ground faults? Surely no. Answer is no. But here it has been framed as a question. If no, then exactly how many distance measurement units will be required for catering to all the tension? Next question is, what will be the setting of the distance measurement unit? How will you set? I told simply Z set Xn for reactance relay, and for the more relay it is Zn cos theta minus tau. But how to do that? Then whether to measure the this is again very important question. Very important question. See, simply I told impedance or reactance. But now the question is, in case of a line to ground fault or double line fault or double line to ground fault, all are categorized as unsymmetrical faults. During the unsymmetrical faults, we used to find the current using the sequence components. So now, whether I have to measure the positive sequence impedance or negative sequence impedance or zero sequence impedance, which one I have to use? So these are the questions we want to answer. Thereby we can understand how to implement, how to incorporate this distance relay for the protection of transmission lines. Okay. So the answer for the question